Listen-only mode.
Hello everyone, welcome to our webinar today, Electrical Safety Testing 102. This presentation follows from our previous webinar, Electrical Safety Testing 101. I want to introduce our team here. I'm Bishan Patel, I'm an applications engineer here, and I'll be a presenter today. I also have Syed Abidi, he's one of our senior applications engineer, and he'll be a panelist for today. And we have Alison Oba, she's going to be an organizer for our webinar. Before we get started on our webinar, there's a few webinar notes I would like to go over. If you have any questions about the presentation or any kind of questions about the material that's being presented, use the question and answer utility, and Syed Abidi will be answering that questions as we go on. If you have any issues with the audio part or any presentation, any issues with that, use the chat box to message to Alison Oba. We also have the webinars recorded and available online on our website. And if you'd like to get a copy of the presentation, you can also email Alison. Her email address is alison.oba@arisafety.com, and we'll email you a copy of this presentation. For today's presentations, we would like to go over some commonly performed electrical safety tests. We want to review what type of tests are considered routine tests versus production line, or routine test versus type testing. We'll also look at some of the requirements that are called out for in the standards. So we'll look at the test requirements. This will be your current requirements, your testing requirements for amount of time you have to test. This could be also including your limits you need to set on your testers. Next, we'll look at finding the right device. Again, looking at the standards, there's some requirements for picking a particular product. It could be a ground bond tester, it could be a line leakage tester, and if you're performing all the test types, you want to probably do an all-in-one tester that does all your tests for you. So we'll be looking into which is the right device for you. Further, or later in the webinar, we'll also be looking at things to avoid during testing. Some of the common knowledge types we'll go over and give you an outline of what to look out for when you're performing electrical safety testing. So here are the most commonly performed electrical safety tests. First one is a ground continuity test. Here you're just making sure there's a continuous path on the ground wire. If you have a three-pronged adapter cord or line cord that has 3 pins on it, usually the ground pin is a round pin, and you want to check to see if that ground pin is connected to your ground on your DUT or device under test. This is a simple test, and it's only checking for a continuous path. Ground bond test is, we'll go into more details, but ground bond test will be more stringent test. Now, we initially check the ground continuity, but the ground bond test is actually performing a stringent test, and we're actually putting some current through it to make sure it's able to, it doesn't break down in the event of a fault that occurs when there is a fault that routes the current through the ground pin. So basically a ground bond test is to verify the integrity of your ground connection. We'll look at dielectric withstand test, also commonly known as a high-pot test. We'll look at what the circuit diagrams are for performing a high-pot test and how a high-pot test is performed. Here we're trying to make sure the insulation doesn't break down. That's protecting the end user from potential shock. So when you're testing your DUT for a high-pot test, you're actually performing a high voltage test to ensure that insulation doesn't break down, the protective insulation. We'll also look at what's called insulation resistance test, also known as an IR test. In an insulation resistance test, you're actually getting a ohmic value for the resistance between your live conductors and your protective insulation. And we'll also look at touch current testing. In touch current testing, you're making sure that when the device is operating, the end user or the end user does not come in contact with any high current when the unit is operating. So if a person was to come up and touch a end device or a DUT, they don't feel the shock of whatever is leaking onto the ground pin. Before we get started, let's clarify different types of testing. There's two common types of tests, type test and routine test. The standards always call out for what you want to do in type testing, and there's a section for routine test. If anything that's not mentioned or anything that's not mentioned in the routine test automatically becomes a type test according to the standard. So if you're reading your standards and the standard has some of the steps you have to perform, and those become your type testing. So type testing are performed in laboratory environment, sample of your products, and the product is still in the design phase. You could also do type testing when you're sending it to the safety agency for listing purposes, and mostly done on a small sample, which gives you a chance to improve your design if you were to find any issues with your product design. And again, this is usually performed in a laboratory environment, or also known when you do a conformance testing. When you do a routine testing, your routine testing is done on your final product. Once it's assembled, when the assembly is done on your product, and finally is ready to go out to end user, you want to perform the electrical safety test on your DOT to ensure any process that you might have during production did not damage the insulation, did not damage your ground wire, did not damage any kind of other electrically safety things you put in there, like the ground wire, basically. The standards do require to have every products that go out to be tested 100% of the time, and this is why we call it the routine test. In the standards, if you follow the standards, there's a section, usually in the annex, will list out the tests that you need to perform doing a routine test. Some of the things I already covered, but I wanted to go over some real quick. Usually type testing is mostly performed in your development stages, and right before you want to get it agency listed, or if you have prototypes that are coming down the line and you want to make sure they're electrically safe. These are more stringent tests. You're supposed to perform the test at a lot longer time frame compared to a routine test. The reason for that is during a lab test, you're stressing the product a lot more compared to doing a production test where the test times might be 1 second. During a type test, that time, the testing time required might be 60 seconds. Again, these are all the parameters of the testings are always listed out in the standards you're trying to comply to, and they list out what the time that it should be tested during type testing and amount of time it should be testing during a routine test. Again, some of the items about routine tests, it needs to be performed by the manufacturer of the end product to ensure that it's electrically safe, and it meets the standards, the tests outlined in the standards for routine test. These are much quicker tests performed, and most of the parameters we get for the routine test do come from the standards. Before we go on, we do want to know if what kind of test you're running during your routine test, which will be your production line testing, and we'll have Allison Oba put up a poll question.
Hi everybody, thank you so much for participating in our poll question. I'm going to go ahead and close the poll question for right now. So as you guys can see, 76% of people in attendance today perform a high-pot test, 62% perform a continuity test, 58% perform a ground bond test, 36% perform insulation resistance tests, and 38% perform line current or line leakage tests. Thank you all so much for participating.
All right, thanks very much for participating. Looking at the poll results, it does look like majority of you are performing the high-pot test, which is one one of the most important tests you could perform on your DOT. This is to ensure that the insulation that's protecting the end user doesn't break down in the normal operation. So if you had a product that was rated for 120 volts, you're just testing this product at almost 1240 volts, or the voltage listed in the standards, to ensure that if there were any transient voltage applied, or if there were any transient voltage coming into the power line, the product is able to handle the transient voltage, and it would not break down, cause any kind of electrical shock situation. And continuity is also a common test performed during routine tests. This is to ensure that the ground has at least a continuous path to ground. Ground bond test is not commonly required, but some of the standards do require to perform ground bond tests during routine testing. This is to ensure that even though continuity is a confirmation of a ground path, a ground bond test actually makes sure that whatever was tested during type testing is also holds up through the production and all the way to the end of the production line. We'll cover some of the other tests later on, the insulation test and the line current test, when we get to that in the webinar. Quickly take a look here. We're going to talk about the ground continuity test. As I mentioned earlier, this is verifying a continuous path between 2 points. So going back to the example of a line cord, a product that's class 1, class 1 products all have the line, the ground pin on the line cord, and this is what you're verifying. You're verifying a continuous path that exists between the ground pin and your ground on your DOT. In case if there was any ground fault, the ground pin is able to, at least there's a path for the current to take. This is usually a low signal, low DC signal is applied, so very low current test. Again, you're not stressing the ground wire, you're just trying to make sure there's a continuous path. For some standard, this is acceptable form of testing the ground wire. For some other tests, you want to do what's called a ground bond test. This is what we'll look at next. So this ground bond test is verifying the ground wire that you have for your DOT is able to handle the current that might possibly be there if there was any condition where the live wires came in contact with the inside your DOT, the live wires came in contact with the chassis of the product. This will safely route the high current to ground. You want to ensure that if your if your product is rated for 15 amps, or if it's going to connect to a breaker panel or circuit where it's connected to a 15 amp breaker, you want to make sure it's able to at least withstand that much, or at least carry that much current to ground. We look at ground bond test. It's also considered a ground continuity. So when you're performing a ground bond test, inherently you're also checking for continuity, because when you're running that much current through the ground wire of your product, you're automatically performing a ground continuity test. Quick look at the circuit diagram for what a ground bond test is. On the left side, you could that would be your high current tester or ground bond tester, which could output high currents, somewhere up to 30 amps or even 60 amps for some standards. You're injecting high current into the ground pin and measuring the return onto the chassis of your product or any metal exposed part of your DOT. You're making sure that this path to ground is at minimum as best less than 200 milliohms. Some standards require this to be less than 100 milliohms. This ensures that if somebody does come in contact with the ground, or does come in contact with your DOT, in case there was a fault condition, the path is not taken through that person and is safely routed through the ground wire. Take a look at a pass condition here. We're injecting a high current from the tester on the left to the DOT on the right. The current is injected at the ground pin, and the current is carried all the way to the return, and the resistance is being measured. Now, if the resistance is less than what's listed in the standard, this is considered a pass on a ground bond test. When you have a fail, what this indicates is either the ground bond, the reason the ground bond failed is that the resistance to ground was higher than what was listed as your limits or what was required in the test standards. So, for instance, if the resistance, when you're outputting 30 amp when you're performing a 30 amp ground bond test, if the resistance of the ground wire was higher than 200 milliohms, this would be considered a fail, because this would be a higher, it would be a higher resistance path to ground, and would not meet the standards. Quickly take a look at how you would use it on a product. So if you had a line cord that plugs in, or if you had a line cord a line corded product, you would plug it into an adapter box, and the high current is injected on the ground pin, and your product is tested at the chassis point of your product. The return is taken at the chassis point of your product. Some of the other items to go over here would be how do we get to the parameters that are part of the ground bond test. When you look at your standards, the standards usually list out the current that needs to be applied to your ground pin and the resistance that needs to be measured. For example, a standard UL 60950 for IT equipment, doing a type testing, it calls out for test current to be twice the fuse rating. So if your product was rated for 8 amps, 9 amps, it needs to be tested at either 16 or 18 amps, depending on the products, or twice the current rating of the circuit that it's going to plug into. So if the device is going to be plugged into a 15 amp breaker circuit, or meant for an environment where there's 15 amps breaker, at this point you're required to run it at 30 amps. The amount of time that's required to run this test will be also listed in the standards. Most commonly listed time is 60 seconds. Ground mount test is performed for 60 seconds during type testing. Some of the other things listed in the standards are open voltage or no load voltage condition. They want to make sure you're performing the ground mount properly. The voltage should not be more than 12 volts. Some standard listed as less than 8 volts. Some standard listed at 12 volts. Just make sure the test itself does not exceed the voltage requirement. Again, the ground bond test could be AC signal or DC signal, depending on the standard. So this information comes straight out from the standards. The amount of current that you need to apply, the amount of time that the current needs to be applied for, and any other requirements of DC or AC signal. I'm going to quickly show a demo of what we do a ground bond test with our Omnia tester. This is a video that shows us using what's called a line verification, test verification box. It's the TVB2 box that's on the right. Basically acts as a load, and it creates some fault conditions or some pass conditions, to make sure our testers are performing all the pass and fail circuit detection are working properly. So real quick, what we're going to do here is first test, we're going to do a ground continuity. You could see the first test was a ground continuity was a pass, and the resistance reading was 0.63 ohms. This test was ran for 1 second. The next test, we're going to switch over to the ground continuity fail. And in this case, the resistance between the red high current port and the black return port, there's not a continuous path, and the resistance is higher than the set limit, and this would fail your ground continuity test. So this basically indicates, even though there's a path there, it's not within the limits that are required. So ground continuity will fail for that. Next, we're going to perform the ground bond test, and this is we're applying 60 amps of current coming out of the red leads here, applying to the load, which is the resistor that lies between the red test leads and the return lead. We're applying 30 amps of current between the load, and you can see the resistance measured here is 63 milliohms. This ensures that it's less than 100 milliohms, and this will result in a pass for a ground bond test. Next, we're going to see what a ground bond fail looks like on our testers. When you do a ground bond fail, when you apply 30 amps of current, this actually results in the resistance being a lot more than 20 milliohms. Let's take a look at it real quick. On a fail condition, the resistance that was red between these 2 points was more than 200 milliohms. All right. Here's a good visual look at what a ground continuity versus ground bond is. On top, you see the a strand of wire which could be only one, the multi-strand wire which only has one strand connected, this will pass your ground continuity. But when you perform a ground bond test on the same wire, it will fail. The reason for that is that the one strand of wire may not be capable of carrying 30 amps of current that the standards require for. So you might have a continuity would pass for your DUT, but this does not guarantee that a ground bond or is still able to handle the fault currents, which could be upwards of 30 or 15 or 30 amps coming through the breaker. So this is a good visualization of what ground bond versus ground continuity would be. We're going to go into high path testing. Also, so the dielectric withstand test is also known as a high path test. In this test, you're actually performing, you're actually subjecting your DUT. DUT is insulation that's protecting the end user at a higher voltage than the normal voltage that it will encounter during the life cycle. A product rated for 100, if the product's rating up to 240 volts, the standards usually require 1400 or 1480 volts to be applied on the line and neutral shorted together, and the resulting current is measured. And what the standard is usually looking for is either a breakdown condition where the insulation breaks down and causes hazardous situation at that voltage. So when we say high path test, it's a high potential test, and it's a deliberate application of high voltage to make sure that the insulation is able to withstand that voltage. There's a resulting leakage current because what you basically created is a big capacitor. There's always going to be some leakage to this capacitor, but you would have to refer to the standards to find out if the standards are actually calling out for some leakage measurement, or they actually only care for the breakdown. And a breakdown would be like an avalanche of current that flows through the insulation, compared to a normal leakage current would be somewhere in the milliamp range, you know. Take a look at the circuit diagram for what a high path test is. This test is like most of you said, you do perform this test. 76% of the people that took the poll, they say they do perform this test. This is one of the commonly performed tests on a routine test, which is on your production line. What you're really testing here again is your insulation that's protecting the DUT from line voltages. And the way you do that is the way you perform a high path test would be shorting your line in neutral and applying a high potential between these 2 points. If the breakdown were to occur, this would occur within the insulation, and our high path tester usually are able to detect the breakdowns and alert the test operator or somebody that's using the tester to let them know that there was an actual breakdown that happened on the unit. Again, a pass condition would indicate that there was no breakdown. There's nominal leakage current, but there's no breakdown. A breakdown again would be a really high current flow between your insulation. Nominal leakage do range anywhere from 0 to 10 milliamps, depending on your DUT. There's some products that we've seen that could go up to 80 or 90 milliamps. You know, this does not indicate a bad product. This could be just the nature of your product. What the standards usually look for is breakdown happening in your product. And what we mean by breakdown is in the event that applying high voltage to your product results in an arc that happens, and also a really high flow of current that goes through the capacitor that you created. This will indicate that the unit was not able to withstand the voltage that was applied to it, and it broke down under that condition. And this would be a fail according to the standards. The way you perform a high path test would be, again, applying high voltage to your line and neutral it, taking a return on your chassis of your product. This could be any metal exposed product, any exposed metal products, or maybe even the ground lug of your product. The leakage current is present on majority of your DUTs, and most of the time the standards are only looking for breakdown. Again, this test is performed on both Class 1, Class 2 products. For Class 2 products that do not have the ground pin, or they might be some type of plastic products like laptops that have no exposed metal parts, there's different ways to test this. You would test the type 2 products, or sorry, type 2 products would be tested with a return path would be an external representation of a palm. So maybe like an aluminum foil wrapped around some foam placed over the product to detect the leakage current. If the insulation was to break down through the plastic, it will break down and create a create a breakdown condition on your aluminum representation of a hand. Most of the standards do list out if they want to perform the test in AC voltage or DC voltage. Some standards also allow you to perform either one as long as the voltage are converted, the equivalent voltage is converted. So when you're performing an AC voltage, since AC voltage are listed in RMS values, the DC values are always written as a little bit higher than the AC RMS values because they want to make sure when you're performing an AC test, you're performing at the peaks, peak voltages of ACs are considered into when you're converting that into DC voltage. Some of the trip points that you set on your high path test could also let you know about the quality of your product. The standards cares for breakdown, but if you really wanted to know your characteristics of your product that was designed properly or not, you could look at the leakage reading. You might have a design change where the leakage reading went up. This could indicate that there are some components that are not performing properly or they're not insulating properly as they should. So some of the leakage reading, even though it does not indicate a breakdown, could indicate some of the quality of your products they're using. If every product was not designed properly or the quality of the product was not up to the standards, this will result in a higher leakage current being read by your high path tester. There is if the standards don't call out for the test voltages, there is a rule of thumb that we usually use is twice the rated voltage plus 1,000 volts. So product that's rated to operate at 240 volts, you would multiply this by 2 and add 1,000 volts to it. This will be an approximation of what the standards are looking for to apply between at line and neutral shorted and then measuring on the return. So you're applying a potential of 1,480 volts between those 2 points to make sure there's no cracks or there's no pinholes in the insulation that could cause it to break down over the lifetime of a product. We're going to look at an insulation resistant test. This is a test that's performed in a similar fashion, like I mentioned earlier. It's a similar fashion of a high path test, but this is usually a DC test. The standards usually call out for either a 500 volt test or a 1,000 volt test. And in this case, we're measuring the resulting ohmic number. So what is my resistance value for this insulation? When you do get this number, the standards usually call out the low limit of this insulation. They want to make sure that you're protecting the DUT is at least 1 mega ohm, 5 mega ohm, or a particular ohmic number. And in this case, the higher the ohmic number you have, the better the product is. So if you had a DUT that results in an IR test of 50 mega ohms, and the standards only call out for 1 mega ohm, then this results in a much better product. You have a lot better product that is designed, The way the IR test is performed is you're applying a DC voltage, you're measuring the leakage current, and then the leakage current is turned into the actual ohmic value of the resistance, or the ohmic value. So this will actually quantify your insulation's resistance value. It's mostly used in a lot of the lot of standards do require the IR test. It's not one of the common tests, but some of the standards do require this as part of their type testing and routine testing. Quick look at how insulation resistance test will be performed. Again, the test is same test, but in the results we're getting the actual ohmic resistance value of your insulation. Earlier we're getting the leakage value, which was the current that was leaking through the insulation. Now we're getting the actual resistance value of your insulation. And it's not performed at the high voltages we mentioned earlier. Usually performed at low voltage, 500 volts or either 1,000 volts. If you look at the standard EN 60204-1, safety of machinery, it specifies a 500 volt test, and they want to make sure that at least the insulation resistance should be at least 1 mega ohm. So this will be a minimum limit set on your tester. You want to make sure the product you're testing is at least 1 mega ohm of insulation. The resistance value of the insulator you're using is at least 1 mega ohm. Again, the test is performed shorting line and neutral, getting the return on your chassis point. Also have a quick video demo of these tests. If I could get to it real quick. What we're going to perform here, again, we have our test box here, the test verification box, and it's nothing more than just the lowers of some resistors. And we're going to be taking a look at how we perform a pass on a high pot test and what a fail looks like on all these test types. So here you can see we're applying 1240 volts on our red test lead here. The return point is still the same, and the resulting leakage current is 0.609 milliamps. So this test did not result in any kind of high leakage or any kind of breakdown, and this will result in a pass from our tester. So next we're going to try the high pot fail scenario. In this case, applying 1240 volts resulted in a high leakage current. Previously you saw it was 0.609 milliamp. Now the resulting leakage current is almost 10 milliamp. So if you had a product that was previously passing and now all of a sudden you see 10 milliamp of current, you could tell that something's wrong with the product itself. Some components are failing or close to failing. This wasn't a breakdown, so this is not a fail in test standards perspective, but having higher leakage current of 10 milliamps, it will indicate there's something obviously wrong with the product you're testing. Next, we're going to try the DC voltage. Again, we want to do a DC equivalent of an AC test, so we're going to apply a little bit higher voltage. In this case, we're applying 2,120 volts. The resultant leakage current is 1 milliamp. Since this current is within our limits, or the limits that we set on our tester, this will indicate a pass. Next, we're going to make it fail, and in this case, we're going to apply the same voltage and measure the resulting leakage current. And at this point, you can see that it failed at 5 milliamp. So initially we had 2 milliamp of leakage current, and now we're seeing 5 milliamp. Next, we're going to do the IR test. Again, we're going to be applying 500 volts DC and measure the resulting resistance of between these 2 points here. In this case, my resistance reading is 4 mega ohms. Some of the standards require at least 1 mega ohm. So this will be if this was a DUT, this will be a pass. The next, we're going to run a same IR test, but this time we're going to run the fail part of it, and we're going to apply 500 volts again. And in this case, this resulted in only 1 mega ohm of resistance. So this would be considered a fail. Anything less than 1 mega ohm would be considered a fail, because we want the result to be higher than 1 mega ohm. So that was our quick look at how the tests are performed using the tester, and what kind of voltage we apply and what kind of resulting leakage current are normally seen on our tester. Next, I'd like to go into what we call leakage current testing. This is also known as line leakage testing, and this is when you're performing current. You're testing for current on the ground pin or any kind of touch point, and the unit is actually powered on. You want to make sure during the normal operating voltage or during the normal operation of your DOT, there's not leakage current that could be felt by the end user if they do come in contact with your product, or if they come in contact with any of the exposed metal part of your product. So, for instance, if you have a toaster at the house, there's going to be some leakage current to the ground point of the toaster or even the metal part of the toaster, but the standards call out for how much this leakage current should be. We covered in our previous webinar of types of current and the values of current that are perceivable by um, human beings, the value of this current. And some of the standards list out the leakage current to be less than 5 milliamps, but I've seen it go lower than that for leakage current testing, as low as 0.5 milliamps, so 500 microamps. So some of these numbers do come from the standards. The standards require you to do, depending on the standards you're complying to, will list out the required acceptable amount of current that could be under your ground point or ground wire. And this is actually your testing. Some of the requirements do say that you want to test a product at a little bit higher voltage than the normal rated voltage. So this just to ensure that if there's any transient or if there's any unbalanced power, if the power is not exactly at 240 volts, it still doesn't cause a potential hazardous situation. For instance, a product that's rated for 240 volts, the standards will actually call out for you to apply 10% more. So 264 volts needs to be applied to your product to ensure the resulting leakage current when the DOT is actually operating, it's not harmful for somebody that could come in contact with the DOT. This test is required on majority, or actually all of the medical equipment that's out in the field. The point being that the medical devices do come in contact with patients, and they're also more stringent about the line current test, or leakage current test, sorry. There is also more tests required, more than the leakage current testing, but in the medical devices, there's a lot more tests involved when you're testing to different points of your device, different applied parts, and we're measuring all the resulting leakage current to all these points. Again, this will be covered later in the year when we go over our actual webinar that covers the leakage current testing. We actually have a full webinar that covers all test types in detail, especially for our medical industry, where we're showing all of the tests that could be performed for your leakage current testing or line leakage testing. Quickly take a look at the circuit diagram here for leakage current testing. What we're doing here, we're actually powering up the instrument, let it settle, let it be under normal operating mode. You want to make sure the device is turned on with the on switch, and it's past all your boot up sequences and everything, and now it's operating under normal conditions. You're going to measure, the leakage current is measured at a metal chassis point or a ground point on your product, and we're going to put a measuring device in line to measure this resulting leakage current. The measuring device is made out of or equivalent resistance of what a human body would look like that comes in contact with the DOT. So next we'll take a look at what the standards actually show for a measuring device. On the right you can see the equivalent circuit of what MD is as referred to in the standards. The measuring device refers to this is an equivalent circuit of what a human body impedance would be when it comes in contact with any kind of electrical circuits. And this comes from 60601-1 standard. This is the actual circuit that they will want you to test, and this will be the MD that are part of our test instruments that measure the current going through the measuring device itself. They do vary between standards, so the measuring devices do vary from standard to standard. Some of them do reference some other standards, and if they don't clearly state the measuring device in a particular standard, they usually refer it to a different standard or a particular standard that might be that already has this measuring device listed out. Um, our instruments do carry majority of the measuring device listed in the standards, and we also have a space to design your own measuring device. If you had some requirements that are a little bit different than the standard measuring device requirement, you could actually make your own network of resistors and capacitors, and what we call an external MD, which is designable by you, and we could still use our testers to test those. Time for our second poll of the day. We have question is, how do you select your safety testing equipment? Things we want to know is how do you come in contact, or how do you get specifications of what kind of tests you're performing, and who makes the selection based on what kind of parameters. So I'll have Allison put up a poll.
All right, everyone, we asked you, how do you select your safety testing equipment? Please choose all that apply. I'm going to go ahead and close the poll question right now. Sorry, technical difficulties. All right, so based on your participation, we see that 82% of people choose their safety testing equipment based on testing standards directly from organizations like UL or IEC. 31% follow what is specified by their company. 9% say their instrument is usually inherited from a different group within their company, and 18% usually look for a CE mark located on their tester. Thank you guys all so much for participating.
Okay. Again, thanks very much for participating. Looking at the results, it is true that standards usually call out for some of the requirements for your testing purposes, but the standards usually are broad standards, and these are what things that minimum requirements you want to meet. There's also some of the participants, they also have company requirements that might be more stringent than what the standards require. So that's good to know that there's also other standards that people use that are also what we call standard specified company standards, internal standards compared to external standards like the safety agency listing. We here at AR actually have a group of applications engineers. There's 4 of us here that actually will look over any kind of information that you might need. If you had any questions about any kind of test voltages as pertains to a particular standard, or how to perform a test properly, we offer that service to our end users that buy our product as part of our service. We do carry a full line of testing products. For electrical safety testing, there's actually a section in each standards that applies to electrical safety testing. So when it comes to ground mount testing, we have standalone ground mount testers. When it comes to dielectric withstand test, also known as high-pot test, we sell high-pot test by itself. We also sell line leakage testing or line leakage current testing testers by standalone testers. And then we have our all-in-one encompassing instrument that could do all tests, 6 test types. You could do your AC test, you could do your ACW test, DCW test, which are your high-pot test. You could do ground continuity, ground bond test, and also do line leakage test or leakage current testing in the same unit. So we have a variety of instruments. They're also CE listed, so that ensures that we went through the same process as your DUTs would go through for getting CE listed. So they're tested for all the electrical safeties themselves. We also provide additional features like scanning matrices and software to automate this. So we are your resources. If you have any questions, even before purchasing our instrument, if you have questions about standards or how to for your particular application, how to perform a test, we're here to answer those questions, and we'll include those contact information later on in the webinar. So how do we find the right tester? Like I mentioned, and majority of you already are looking at the standards. The standards will dictate what kind of output currents you need to have, what kind of limits the instrument, the tester needs to have, and what kind of tests you need to perform. So a person that, if a standard is requiring you to perform all the test types listed here, your ground mount test, your high pot test, your IR test, your line leakage current test, then you want to buy an instrument that is able to do all these tests at one time. You might also have a situation where you only want to perform one particular test. So if it's only a ground mount test you want to perform, you don't want to buy the instrument to perform all the tests. So in this case, you would buy a standalone tester, and that might could go up to 60 amps. So a particular standard might call out for 60 amp ground mount test. So you want to closely look at your tester specifications and make sure you're able to set your limits or set the output limits correctly. There's some standards that require 15,000 volts being applied. This applies to different categories of DUTs, but some of the commonly known high-pot testers can output more than 5,000 volts. So you want to be looking at where your DUT falls in, what category according to that standards, and find out what voltage those needs to be tested at, and make sure the tester is able to perform that. Some of the standards also require what we call a 500 VA requirement. And the 500 VA requirements is to ensure that each standard is capable of outputting at least of 100 milliamp of current, to make sure some of the testers that can't perform this are not falsely passing some test. The 500 requirement is listed out in some of the standards, and some of the standards do make an exception to the 500 VA requirement as long as you have a voltage meter or something that's measuring the voltage across your DUT. So all our testers come with a voltage meter already built in. So if the standard does have an exception for 500 VA, all of our testers will qualify for that. Some other stuff to look at, I already mentioned some of these items here. If you have any questions about it, you feel free to give us a call, or have one of our contact information and contact one of our applications engineer, including me, and we'll answer the questions for you about test types, test limits, how to perform a particular test, and any other issues you might be having to perform a particular test. We have instances where the standards will require for you to do an ACW test or AC high-pot test, but there's also a section that you could do a DCW test, which is a DC high-pot test, and we'll look into depending on the DUT, the DC test might be better. So we'll look into the standards for you to see if it's acceptable for you to perform this test. We'll also ensure that you're performing your test correctly, and this goes along making sure you find the right tester and get the correct parameters for your testing setup. I want to quickly go over things not to do when you're testing. Some of this stuff might be obvious things not to do, but when we do our company visits, we have seen things there that doesn't make sense around the high-pot testing area. Starting at the left, I never seen anybody touch a DUT during testing. Well, not the high voltage part, but I have seen the operators touching part of the DUT. So not realizing that at any point in the case of a breakdown, that part of the circuitry might also energize. So in this case, you want to make sure the operators never come in contact with the DUT. You want to use things like a DUT enclosure box, anything to prevent the operator from touching the DUT. It seems like an obvious thing not to touch something under test, but they don't realize that the voltage that you're testing this at is pretty high voltage, and then also the current that it could output is lethal. I mean, it's pretty, 10 milliamps of current is definitely something you will feel. So that is an electrical current that you could feel. Next, we look at the smocks, the ESD smocks. That's something a big no for high-pot testing stations or electrical safety testing in general. What the ESD smocks would do is actually ground you and ground you as a person, but we want to make sure you're not grounded. You want to be away from the ground potential, so the current has no path to ground. And the high voltage, if you did come in contact inadvertently with the high voltage, you're not performing. There's no loop for the current to flow through you. So you want to make sure your ESD or ESD areas are away from high path testing, and definitely no smocks or ESD smocks in the area where you could potentially ground yourself and cause any electrical shock situation. We also have issues where the end users are using the high path test leads live. So in case where you need to perform high voltage testing with the leads coming in contact with the operator, you want to make sure they have personal protective equipment like high voltage gloves, things of that nature, to make sure they're not coming in contact with the high voltage, and you want to make sure the operators are safe. You could also find equipment that has a broken ground pin, and broken ground pins are if the person that's looking at it doesn't understand it, it could cause a big potential for shock hazard, where it's meant to I guess it's meant to divert all the fault current to the ground pin. But if there was no ground pin available, or if there was no ground available for the fault current, and it will be anybody that comes in contact with the DUT, this could cause it to use the path to the person will be used. So you want to make sure all your testing equipment, all your DUTs, the ground pins are properly in place, and all the proper connections are made to the testers. Again, breaking off a ground pin is not something you want to do especially on a high electrical safety testing equipment, but this also applies in general. There's a reason to have that ground pin in there, is to protect in the event of a fault condition where the current needs to route to ground, and it's going to take that path. So breaking off a pin would cause all that current to be waiting to find a different path to ground. And if a person does come in contact, this will be the path to ground. So some things to avoid. I discussed some of this already, but here's a good list of things not to do or what to avoid during testing. You want to make sure you're familiar with the instrument. So when I mentioned earlier about when you're picking out your instrument, you want to make sure you're also aware of what kind of current it could output, what kind of voltage it could output, and any kind of safety features that it might have. So you want to read the manuals or instruction guides in the manual to make sure you're safely setting up your workstation. You don't want to ever use the equipment that you're not familiar with. If I'm using a ground mount tester that could output 60 amps of current, not knowing what a 60 amp current means, I would not want to be near that instrument. I mean, that's potentially a huge amount of current flowing through either a person, or even your DUT could be damaged. So you want to make sure you're testing properly with proper rated voltages and currents, and even making sure that the instrument you're using is within the specifications. So another list here would be making sure follow the guidelines in the manual, things like the broken ground pins or any kind of ESD stations that we mentioned earlier, or you might want to make sure that the unit itself is calibrated. You want to make sure we recommend a yearly calibration, since these are measuring instruments. They could be off, and even the output could be off. So if you're applying 1,000 volts, and if it's not calibrated in 5 years, you don't know if that 1,000 volt is 1,500 or 900 or 800. So in that case, you want to get things calibrated with the recommended calibration cycle by the manufacturer. This could also protect your DUTs from being sent out damaged. So if your calibration is not up to standard, potentially send your DUTs out in the field, which could be damaged, and you might have costly recalls. That might be something that comes out of not having properly calibrated instrument. You want to also be aware of the environment you're testing it. I've been to a site where there's puddle of water right around the high path testing area, and the operators weren't aware, or they actually walked through this water to get to their station, and there's still water around the high pass station. So you want to be aware of any situation that could be considered a hazard situation when you're working around electrical equipment. Some of the other points here is you want to make sure that when you're modifying the cable or test leads, you modify according to what the manufacturer recommends. You don't want to be buying products that are not rated for the voltage it's going to output. You don't want to buy a high voltage lead that's rated for 1,000 volts when you're going to be the tester could output up to 5,000 volts. So you always want to make sure the ratings are followed for your test leads or any kind of connections you're making, custom connectors that you might make. Again, also want to make sure that accessories, like if some accessories that came with our instrument, and if you were to purchase some other accessories, you want to make sure it at least meets the minimum standards of what the accessories you had with the tester, and using any other accessories might be harmful to the operators, or it could be damaging to the tester itself. So that was our webinar today, and if you have any questions that were not answered by Syed during with the question and answer session, you could ask them now. I could try to answer any questions you might have about the material or anything else in general.
Bishan, there were a couple of really good questions on the chat line,
Okay.
which I think would be great for everybody to hear. One of the questions was regarding the use of ESD smog while using, it was asked about while using the Omnia, but it applies to more in general, like testing.
Sure.
So basically what we want to make sure is that everybody knows that ESD smogs will, or using the ESD smogs will basically put them at ground potential. And that's something that we want to avoid when we are performing these high voltage tests, is to not be at ground potential, because then we're providing a path for any fault currents to flow to ground through us. So that's the big reason why ESD smogs are not recommended. And the other thing is, from our testing, some experimentation with ESD smogs, we know that they easily catch fire. We tried to high-pot test a ESD smog and it caught fire pretty easily. So those are the few important points to remember in why we don't recommend using the ESD smogs with any electrical safety testing, is because you don't want to be tied to the ground.
Correct.
The other question that you want to go over is somebody was asking about what if their product has multiple points that they need to test. So you can mention about the scanners a little bit if you want to go
Sure.
talk about that.
So if you did have multiple points, test points, and some of our customers do have it, we usually recommend a scanning matrices where it's able to switch between the high voltage points and return. So if you had a scanner that had up to 16 channels, you could connect each of those channels to a test points, and you could switch between, our testers are able to switch between those test points and get the resulting current or resulting readings. This ensures that your operator is not switching out test leads every time they have to run a second test. So it makes it a lot more safer for them to perform this test when you're doing multiple point testing. There's also automation where you could have a particular test performed, then the interlock. You could have an interlock system where the test is not outputting anything. The tester is not outputting anything when the operator is switching between your test leads. So you would have to set that up in your test sequence, where having two separate testing points make sure that the interlock is broken between the tests and there's no output coming out of our tester. So that's a safety feature on a tester, where once the interlock is broken, there's no way the tester is going to output any voltage. So if you had multiple test points, you could either use scanning matrices or make a system where between test steps you're able to disconnect the test points and try different test points. I did want to mention one thing. We have in the handout section here the AR standards guide. I'm going to quickly pull that up on our website. It's a downloadable guide for safety standards. This is something that we went through each standards to get some quick information, and you can see what standards we reference here. We have the IEC UL 60601-1 third edition. We also have the 61010-1 third edition and 60335. So multiple standards are used to come up with a standards guide. And what you want to do is find the standards you're actually complying to and look at the relevant information about the section that it applies to you. So for section, if you take a look at here for 60335, sorry, 60335-1, fifth edition, it'll tell you the requirements for your leakage current testing. It will tell you the requirements for the high pot testing, and also it'll tell you requirements for other like a ground bond test and things of that nature. So here, continue on to the guide. There's other information further down, and also the recommended instrument that is able to perform all this tests. So we make it a simplified guide for our customers, where if they do have to test to a newer standard or a different standard, they could quickly reference this. And if they did have any questions, you could contact one of us, and we'll gladly help you with figuring out the right testing parameters for you.
Hey, Bishan.
Yes.
One more question that I feel important just came up on the chat line is this Ronnie Cotton is asking, how do I perform a high-pot test if I have relays that must be powered up during the test? So you want to talk a little bit about the hot high-pot test, and then we can send more information, email more information to this this person.
Sure. Now, what we have seen in the field is if the relays need to be if the relays need to turn on for your high-pot test to be performed, then we have seen where manual they'll short out the relay for the high-pot testing purposes, and then they'll remove it after high-pot testing. There's other ways around this. So it's also called a hot high-pot testing, and at this point, your DUT or device under test is actually powered up and is running normally, and then we're applying a high voltage through an isolation transformer. So what a hot high-pot does is you power up your instrument normally, it's running normally, and now we're applying high voltage to an isolation transformer and measuring the resulting leakage current. During the webinar, the high-pot test I mentioned is that does not turn on the instrument, so the instrument never powers on. But a special scenario where you do have relays in place, but they don't come on until you apply line voltage to it. We've seen it perform two separate ways. You could either perform, if you're able to manually set those relays properly for the power to make it all the way through the end. If you're not able to do that, you want to perform what's called a hot high-pot test. In this case, you're actually powering up the DUT and applying high voltage. So we'll send you some more information in email. If anybody else likes same information, please include your email, and we'll include information on hot high-pot testing. Okay, just real quick, I think all right, so here's our website, arisafety.com, for training resources. We include previous webinars, and also we have our white papers that answer some of the common questions, and also contact information for us or anybody at this company. The next webinar is going to be Wednesday, April 13th. This will be going into more details of each type of test. So we'll be looking at the actual circuit theory behind high-pot testing, or all the safety testing. All right, so thanks everyone for joining. Unless there's any other questions, we'll go ahead and like to end this webinar for today, and see you next time.